value can they offer? I mean, why do we use these models? How, what sort of substance do they deliver? What sort of attractive features do they have when we use them? Can anyone tell me? Like, why do we use them? I've kind of alluded to this, but I want to ask you, why use them?
For better understanding of the real world?
Yes. Good. Better understanding of the world. That's right. Understanding the way the world is right now, explaining phenomena that we see. So that's an extremely valuable use of them. Very good. How about another reason? So one is sort of explaining the patterns we see in the world right now. Why might we be seeing this sudden rise in the number of the sort of how the response time in our server farm, if I want to use an example from CS. Why are we seeing this inability for projects to deliver software on time? To use another example. Why are we seeing larger number of West Nile cases in the province in the past 3 years? So that would be explanatory. What's another use? Okay, how to intervene. So what would be the best way to change something about the system? This has to do with decision making. Visual understanding. So giving particularly people who are not from CS background, not from engineering background, not from any technical background, an ability to understand what's going on with the system and why, perhaps? Like what's driving why are they seeing this certain pattern? It turns out these models can be extremely valuable for that. To help them ask what-if questions. How would things be different if this was the case? To provide a visual understanding of that they can't get just in the world. After all, that's what we use maps for a lot, right? We want to see big picture what's going on with the city. These systems allow us to see the forest and not just get caught in the trees, right? So that's very, very important. How about another reason? Prediction. We want to anticipate what's coming down the pike in another few years, in another few months, in another 10 years, if we don't change things, for example. So we want to look forward and with some degree of confidence. And going forward, someone once said, forecasting is hard. Forecasting is kind of another word for prediction. Casting, you're sort of trying to understand what's coming ahead of us. And they said, forecasting is hard, especially if it's about the future. So it's very hard. And one of the best ways to do that is if you could capture regularities. Could we forecast without a simulation model? Yeah. Sure, we could try. And so for example, we meet with people from here on campus. They come to our lab and talk about their needs. And there was one group that came and said that they're involved in building dialysis capacity, so places to treat people who have so-called kidney failure, whose kidneys get to the point where they fail. And to try to figure out these things, they would take a model. They could take a model, a statistical model of the number of kidney failure cases in recent years, and they could take a linear regression on it and say, okay, it's going to be doing this in the future. Now, they could extend it forward, they could extrapolate, in other words, going forward. What's the limitation of that?
You can do changes that happen outside of the stack.
Yeah, exactly. So this doesn't take into account, well, how many people are moving into the province, how many people are leaving, perhaps issues having to do with the healthiness of the people there, how many diabetics are there, which is a big driver for how many people get kidney failure. After all, if there's more and more diabetics coming along, this may end up going upwards after a while. It doesn't capture the underlying structure, the regularities that are driving this. If we want to understand those regularities, and particularly if we want to change them, and to understand how that change will have an effect, ladies and gentlemen, we need something that will capture kind of, as I said, the drivers, capture what's behind this. This is data. That's great. It's great data. Gives us some understanding of how things are occurring over time. But if we understand we want to understand what underlies it. Why is it going up, right? What's the cause for that? And the more and more we understand about the cause and the causal linkages between what's causing what between the various factors, the better we could say with confidence how this will change in the future, whether it's going to go like that, whether it's going to go like this, and critically, how will something we do make a difference? So if we have a big initiative to help kids eat more healthily, or to help encourage physical activity among, older adults, how soon will that affect? How big will that effect be? To do that, we need a model that somehow links these pieces up. No, it doesn't just project. Okay? So forecasting is a great example because so much forecasting is done statistically, but in the worst case, people say it's a bit like trying to drive looking out your back window. You're trying to drive forward, but with data that's all about the past. Kierkegaard said something like, and I wish I remembered the translation of his exact words. He said something like, one of humanity's greatest difficulties is that we live forward but think backwards, or something like that, or remember backwards. So there's a risk if we're not capturing the underlying causes for what's going on, for what we observe, that we're going to be missing out on or we're not going to anticipate when something hits us, and we're not going to understand what we can do to change things, which is one of the most important things of all, right? So this is a very important issue with forecasting. But how about other uses of models? These are great. And I'm indebted to you folks for mentioning. But how about other uses of models? I'll put out a couple more. How about helping to prioritize data points? Helping to tell us which uncertainties really matter for the things we care about. A model like this, it brings together a representation of what depends on what. So we have uncertainties in some of those things. They may matter a lot more than other uncertainties, it turns out. We may have a broad range of uncertainty about a lot of things, but some of those matter a lot for our choices to be made, and some matter very little. This is a big, pronounced feature of these sort of systems. Another use of models. To refine and advance our understanding collectively. Ladies and gentlemen, the statement has been made provocatively, if you want to view it as such, although I think it's actually increasingly accepted, that why model? Because we are always modeling. We're always modeling. Whether or not there's a computer around, we're modeling. Long before differential equations were invented, we're modeling. Where are models? They're simplified representations of what's going on in the world that we carry around. Now, that's great. We reason about, how will things be different if I open the windows of my house? How will that affect the temperature in the winter, right? We reason about how will my car behave if I tap on the brakes when I'm driving. We reason about how long will it take me to get in, how quickly are the buses running, given that it just snowed and I got to get in for my PM class. We're reasoning about these things. We have some sort of model, simplified representations of how things work, how bus schedules depend on snow, and how temperature depends on having a window open or what have you. These are simplified models. So that's great. We reason about those all the time. But ladies and gentlemen, there's limitations to those models. Models we carry on our head. Among other things, we're not very consistent about using them. We forget them, we distort, they depend on how tired we are and how consistently we apply them. They're not very precise. We may know, the temperature based on, maybe we've taken a heat transfer course in mechanical engineering, and we know, we understand how heat flows, we know the heat equation, and we understand how it flows in a homogeneous medium or what have you. When we open the window we're not very good at like calculating. Most of us aren't great at calculating even decreasing exponentials over time, much less highly coupled sets of nonlinear differential equations. And so we end up being pretty bad in our guesses. And it's the same thing with pilots piloting a plane, people controlling a power station, nuclear reactor in Japan, people trying to even pilot a truck driven on ice or something like that. These are things which we have a mental model for how things work. And ladies and gentlemen, the thought here is that by making models explicit, it allows us to share them, critique them, refine them, and ultimately advance our understanding over time. Okay? By taking them purely out of our head, you see this all the time in social debates about social policy, and one group will say this thing is the underlying problem, this other group will say this other thing, this other group will say the other thing. And it really helps if you can actually capture it and have them actually write down and draw out what they mean and sort of in more explicit terms. Maybe it's a qualitative model like that. Even better, maybe it's a quantitative model. It allows them to sort of take it and compare it with the evidence in a more objective fashion and maybe simulate it and see how consistent it is and combine together elements of multiple models to give a more complete picture. These are all part of the scientific dialogue, and the sooner that we can do that, often the sooner we can advance understanding. So within our broader sort of work in terms of advancing shared understanding of real problems, being able to share models and make them explicit, take them out of just our head and put them into a form we can express explicitly, even if it's not totally quantitative. It's an advance. It gets us somewhere, okay? It helps that sort of collective discussion of what's really going on. Lets two people with different views see where they differ and work to resolve those differences, work to improve their common understanding of what's going on, okay? So those are some reasons about why we model. If you go and you look at, I think it's Don Burke's site from University of Pittsburgh. He has a talk on 25 reasons we model, something like that. It enumerates these. And maybe getting them confused with Josh Epstein's talk, both of them that sort of comment on why we model. And actually, I think I heard Don Burke describe it as Josh Epstein. So Josh is at Johns Hopkins, and he has a discussion of sort of 25 reasons we model. And you'll see there's actually all sorts of reasons. Sharing it with non-technical stakeholders, everything from that to issues of, because we automatically are modeling, we might as well be explicit about it. We might as well be careful about it. Might as well be doing it in a way that's sharing it. So these are some reasons we model. That's great. And I appreciate you taking time. So any questions or comments that we want to go before we actually dive into some software and take a look at some models? Questions? Comments? Okay, I'd like to take a look at two little pieces of software very quickly, realizing that we have limited time. So the first of them is software called Vensim. I asked you to download it. And I have to confess that I have a than do you. So actually I'm going to finish up this. So